Okay, so I think we can start, right, Enrico? Yes, you're the big boss. I rely on you. So welcome back for this third day. We are halfway through, not yet, but almost. So let's resume where we left off yesterday. I had started to get into the description of the Hartree-Fock theory. I looked at my notes, I looked at the pace of these lectures and realized I was way too ambitious at the beginning, so I'm going to skip all the derivations. I'm going to go straight to the results and their physics interpretation, which is probably what you care mostly about. The notes themselves that I will make available probably by the end of today will have additional formulas and additional elements of proof. It's not usually the full proof, but it's just a few um, sort of milestones to get to the proof. So that will, and there are also plenty of references. I think they have something like 50 references to textbooks and review articles and things like this. So you can always, if you're interested, you can always go there and get additional details. Okay. So we stopped there where in the Hartree-Fock theory of which is part of the energy density functional methods, you make the assumption that the many-body wave function of your nucleus is going to look like this. It's going to be a Slater determinant, that's the name of this thing, in a dimension. So it's going to depend on these single particle wave functions, which themselves depend on the coordinates of the particle, and also in principle should depend on the spins of these particles. But as I mentioned earlier, I will just almost always neglect the spin degrees of freedom just to make it a little bit simple. Those single particle wave functions, they are unknown. They are the ones that you want to determine. And this is how the Hartree-Fock equation comes in, is an equation you have to solve in order to find what those wave functions are. How are you going to define this equation? You're going to require that the energy calculated on the Hartree-Fock states, and this is going to be, you can, and in the notes I actually prove that this object is normalized. It's normalized if, yes, I should say, it's normalized if those single particle wave function are orthonormal. So you will require that those single particle wave functions are orthonormal. They form a basis of the Hilbert space of single particle states. And if those wave functions are normalized, then this quantity here is also normalized, meaning that we have this property here. And the average energy on the Hartree-Fock state is simply going to be given by that. If the many-body wave function was not normalized, we would have to divide by the norm. But since it's equal to 1, we're good. And then we're going to require that the variation of the energy has to be 0. We are going to try to find the minimum of the energy. Now, if you're a good mathematician, you know that this condition doesn't guarantee that there is a minimum. It just guarantees that there is an extremum. We can prove, and I will not do that, but it can be found in several textbooks that the Hartree-Fock solution, the Hartree-Fock solution that verifies that, indeed is a minimum. It's not a maximum. So we're going to require that the variation of the energy is 0, and this means that since the only unknown, so the Hamiltonian is known, this is the thing that I had written yesterday, and this is what depends on your two-body potential, whether it's a Scherm, a Goni, or whether you have a covariant mean field. So this thing is known. The only unknowns are those objects. So you're going to require that the derivative of your energy, the functional derivative of the energy with respect to every one of these single particle states has to be 0. So this is functional derivative. It's a derivative with respect to a function, not with respect to a variable, but this is essentially the same. Well, it's kind of similar. Now, again, I refer to notes that you have not seen yet, but in the notes, I am trying to do this brute force. So I'm actually writing down the energy as taking this expression, substituting this form for the many-body wave function into this expression, and then trying to show you how you would do the calculation directly if you didn't know any better. There are many ways to derive the Hartree-Fock equation. Another popular one is to use second quantization. When you don't take this form for the wave function, you take something in terms of operators acting on some vacuum in some Fock space. Since I'm going to skip the derivations, I'm just going to give you a few elements to go to the results. And one thing I need to go to the results is, and this is mostly to make my life a little simpler, is I will require that those single particle wave functions, I'm going to write them as, I'm going to expand them on a basis. I'm going to expand them on a basis, so I'm going to sum, in principle, this is an infinite basis, and I have some coefficient here, which should be, and let's change the notation. These functions phi n, it's a basis, so I have to take function that I know. So one example of function that I know are harmonic oscillator wave functions. Whether it's a Cartesian harmonic oscillator in 3D, it's a spherical harmonic oscillator, we know that the wave functions of harmonic oscillator are typically some polynomials times some exponential. So in Cartesian coordinates for a 3D harmonic oscillator, this would be Hermite polynomials times some Gaussians. In spherical 3D harmonic oscillator, it would be some Laguerre polynomials. But the thing is, this basis of functions, these ones, this is your basis, and this is known. You know exactly how they look like. So that means that that when you say that this is the unknown in the Hartree-Fock equation, now the unknown goes into this quantity here. And since I have a number of single particle wave functions that I want to determine, this object is a matrix. So now I have to determine this matrix. Okay. So let's go actually here. So again, skipping all the results, just skipping all the derivation, going straight to the result. And the result is the following. The first thing is the equation that you find at the end when you take those few steps and spend a few pages writing the math. You find that the Hartree-Fock equation that you obtain would look like this. It's a commutator of two matrices. This one is the density matrix, and it will be related to the density of particles inside the nucleus. And this one is, it has different names, but typically it would be called the Hartree-Fock mean field. Sometimes it will also be called the Hartree-Fock potential, self-consistent mean field. These are all similar things. So these are matrices, and in my basis, that is my harmonic oscillator basis that I know. This would look like this. I will try not to screw it up. There may be some complex conjugate that I'm missing here, but this is just a spirit. So this density is a function of those unknown coefficients here. The mean field is written like this, where this part is the kinetic energy. Oops, I should not go to. And it is given by this quantity here. So this is going to be on your basis wave function, and then p squared over 2m. And this quantity here is the actual mean field potential. It's the equivalent for Hartree-Fock. It's the equivalent of the Woods-Saxon or the Nielsen potential that I was talking about yesterday when you do phenomenological mean field. Except now this guy is related to the potential, the two-body force that is included here. And so this would be written as Okay, so I'm gonna. And this, if you want to know what it is, it's going to be a double integral of your basis function. I'm going to run out of space. Then you have your two-body force, and you multiply left by J of R and L of R. So this would be your SCURM, your Goni potential. So it's something you know. It's a model that you have for the two-body forces inside the nucleus. Those wave functions, these are the basis wave functions. Again, you know them, which means you can calculate this matrix element of a two-body force. And you, if you know the density, which depends on this, you can calculate these fields, and so on and so forth. Now, what is the practical, let me back down. At this point, I just say, oh, I have to solve this equation here, and these objects are matrices. In quantum mechanics, at the beginning, we are told that if you have a pair of observables that commute, what can we do? Yes? You know it. Or you knew it. Perhaps you've forgotten, but you knew it. If you have a pair of observables that commute, what is the consequence of that? What? Yes. You can find you can diagonalize those things simultaneously. You can find a basis in which both matrices are diagonal. And that's one possibility that we can use to solve this equation. So the way it works is, it's going to be called a self-consistent loop. So one thing is you have to start somehow, because the trick here is that everything depends on everything else. This mean field depends on the density. This density is unknown. So how are you going to solve that? You take a guess for the density matrix. And let's say this would be your density matrix at iteration 0. With this guess, you can calculate this object. So now you calculate your mean field potential at iteration 0 from this formula. Everything else is known. You have, again, the basis functions are known. Well, this is a Laplacian, you know how it works on the basis, you know your two-body force, you have taken a guess for the density, so you can calculate your mean field Hamiltonian or your Hartree-Fock Hamiltonian at iteration 0, and then what you do is you diagonalize it. This would give you a new set of wave functions. This would give you your Hartree-Fock. So what kind of notation should I use? Actually, this is going to give you some eigenstates, which I can write like this. And so this so actually, let me write it specifically. So you're going to find that H, you're going to solve this equation. You're solving it in a basis where this is the matrix in that harmonic oscillator basis, for example. But you are getting, and if you write a code doing this, you would get all the eigenvectors at once, so they would form a matrix of column eigenvectors. But you're basically getting this as at iteration 0. From this, you can remember that these eigenstates are written in the basis that you know as, I took the, from this you can recalculate the density. And the density now is going to be this, just as before, except that your D, I'm pretty sure there should be a star here. your D now is at iteration 0. And that defines a new version of the density at iteration 1. And then what you do is you go back there. And you keep going until between 2 consecutive iterations, say, so you decide to stop when, let's say, this is one possibility, when the density between 2 consecutive iteration doesn't really change anymore. So it's less than some number that you specify. So you can calculate the norm. There are different criteria to stop this loop, because if you didn't set up a criterion like this, you would go on at infinity. But when you are satisfied that your density doesn't really change anymore, you have reached convergence. Congratulations, you have converged to the Hartree-Fock solution. And by definition, this means that this equation is satisfied. And at the solution, at this Hartree-Fock solution, you have now the density. You have actually lots of things. And once you have those things, you can stop doing stupid math and computing and do some physics. So one of the things you have is you have your density of particles. So you have your density matrix at convergence. You can turn it into a function of R just by doing this. On your basis. So now you have the density of particles. With this density of particles, again, you can show that you can calculate expectation value. If you look at any operator, remember that in quantum mechanics, an operator, especially a Hermitian operator, is associated with an observable, something you can measure. So if you take an operator O, and you calculate the expectation value of O on the Hartree-Fock ground state, we can prove that this is nothing but the trace of the matrix of the operator times the density in your basis. So if you have the density in your basis, in whatever basis you decide to use at the beginning, once you have fully determined this density, once you choose an operator that you're interested in, let's say the radius, you're interested, this is just one example. Let's suppose that the operator would be the root mean square radius, which means nothing but R square. That's an operator. You can calculate now the expectation value of your R square, which is the root mean square radius. And then this could be given by the trace of R square in the basis. So I'm going to write it like this. It's one example. No? The point is that any expectation value of any operator of interest on the Hartree-Fock's ground state is going to be a function only of the density of particle, which is what you get once you solve the Hartree-Fock equation. Okay. If you're interested in comparisons, you also have the mean field potential. So just like the density, you can turn your mean field into a function of R, and you can visualize what it is. And you will find that for typical two-body forces like Skerm-Goni and company, whatever that is not completely crazy, your Hartree-Fock mean field is going to look pretty much like your usual mean field potential. Actually, I should say the mean field part is this component here. It's the Hartree-Fock Hamiltonian isocontained the kinetic energy. The mean field part is just the potential part, and so the potential part is going to look like the usual thing, and that here, so this is going to be of the order of minus 50 MeV or so. This will depend a little bit on the potential, on the two-body force that you use, but so you can compare your mean field potential that you have obtained self-consistently by solving the Hartree-Fock equation with your phenomenological potential of preference, let's say with Saxon also. Now at this point, you may have lost track of why we're doing all of this. The reason why we're doing all of this is we're still interested in fission. This is still a lecture about fission. So we wanted to calculate the deformation properties of nuclei, not from this liquid drop plus shell correction formula, but directly from some knowledge of a two-body Hamiltonian. So how are we going to do this now? Let's see, what can I erase? So one strange property of the Hartree-Fock equation is it's self-consistent. Yes, sorry. Can you give me? So the question is whether we can, whether the Hartree-Fock equation change if we define the many-body wave functions in a different way, not using a Slater determinant. But what kind of what do you have in mind? So a linear combination of Slater determinants, right? Yes. Yes, people who do the few people who do shell model would use Slater determinants as a basis to build to find the solution of which of the things that I erased now, but the eigenvalue problem for the many-body Hamiltonian. So Slater determinant can be used as a basis where you will change the so this single particle state, there is an infinite number of them. When you build the Hartree-Fock solution, you only take the A lowest. I also skip those details, but if you want to build excited states, you will take additional ones and you will populate those ones, and then you have a basis. We will see in 5 or 10 minutes what happens when you take a very, very specific linear combination of those Slater determinants and you introduce pairing correlations. If you take an infinite superposition of Slater determinants, then you do the nuclear shell model. Yes. Very good question. It's up to you. One very good way of doing it is you solve the Schrödinger equation for, let's say, a Wood-Saxon potential, even the harmonic oscillator, a Nilsson potential, something like this, which is not self-consistent. So when you solve this Schrödinger equation, you will obtain a set of single particle states, and you can build then the density. So let's say you have, I will take yet another solution, another notation. So let's assume that your phi n are the solution of the Schrödinger equation for a potential which is, say, Wood-Saxon. And so you solve this with a computer code, and you get those wave function, and now you calculate the density of particle as a sum from 1 equal A to A of this, and this could be taken as your iteration 0 for your self-consistent loop. You would turn this into the basis, but you know, the spirit is you would take this as iteration 0. That's usually what people do. And which potential is up to people's preference. Excellent question again. You guys are in good shape today. So yes, there is always so first of all, you never find a global minimum. Mathematically, I don't know whether there is a global minimum for such a problem like this. You always find the nearest local minimum to wherever you start from. Imagine, so now this is exactly like a minimization of a function. So let's say you have a one-dimensional function of x, and you're trying, let's say, I don't know, it looks like that, and you're trying to find the minimum of this function. And it's actually defined on the full R space. So is there a global minimum? I don't know, but Suppose you use the Newton method or something like this, and you start here. Most likely, you're going to find that point. That's a local minimum. This one is lower. If you want to find it, but you started from here, it's going to be very difficult for you if you start here to find this guy. You would have to find closer to it. And so the problem in these calculations is that the results that you obtain are very often dependent on the initial guess that you take for the solution. So that's what practitioners are always fighting with, is mitigate this risk by trying to be smart about the initial point so that we converge to where we want. That's a practical difficulty. There was a second part to your question, I think. No? That's it? Okay. Yeah. So it is the formula is going to be very useful if you decide to solve the Hartree-Fock equation in a basis. You can solve the Hartree-Fock equation directly in coordinate space, in which case you don't introduce any basis, and that is not really, you would not calculate a trace, or let's say, it wouldn't be the same thing. You would, if you were doing things in configurations, in coordinate space, then your expectation value would be the integral over space of your operator, which is now a function of r, times the density. It's kind of a trace, but not the mathematicians would not really agree with that. So yes, for every time you solve your Hartree-Fock equation in a basis, people will use the trace, because you'll have a code that set up your basis, and whatever programming language you use, you may have some functions that return the trace of a matrix very quickly. So this is a convenient way of doing things. But if you choose to do it in coordinate space on the lattice or something like this, you would have the analog of a trace, but it's not technically a trace. More questions? Nope. Okay. Oh yes. So what I wanted to say is the and I think I can. So one property of the Hartree-Fock equation is that what's going on? I think he started everything. If you where you figure it out, I will continue. So one property of the Hartree-Fock equation is, because it's self-consistent, suppose that the very first iteration, and it always comes back to this problem of the initial guess. Suppose that you choose a density that is not rotationally invariant. That is some corresponding to, if you plot, if you visualize rho of R in 3D, you find that it has a, it's like a disc or a football ball or some, American football ball, a rugby ball or something like that. What happens? That breaking of rotational invariance is going to propagate all the way. If your density if your initial density is not rotational invariant, then your initial mean field is not going to be rotational invariant. Then the wave functions are not going to be rotational invariant, and the density at the next iteration is not going to be rotational invariant, and so on and so forth. And your final solution is not going to be rotational invariant. Why is that strange? Because your initial Hamiltonian, the many-body one, the one that contains the skirm and so on, is rotational invariant, which means it commutes with the angular momentum operator. But if you choose to take an initial density that is not commuting with J square, then your mean field Hamiltonian and j squared are not going to commute. And you're going to get deformed solution by magic. You're going to get the deformed solution that guarantee that the energy is a minimum. So this is a very important difference between self-consistent mean field and the phenomenological ones. In the phenomenological mean fields, you have to input the deformation, and whatever you get is dependent on those inputs. If you choose a spherical shape, you get a spherical solution. If you choose a shape that is only quadruple deformed, then you get a quadruple deformed solution. In the mean field, you start with a guess, but then the self-consistent loop does its magic, and at the end you get whatever minimizes the energy. You may have started with some quadruple deformation that is 0, but if the self-consistent loop so decides, you may find a solution that has a non-zero quadruple deformation. So this is the power of variational principle, is all the deformations are going to be automatically set based on whatever minimizes the energy. So this is actually great for ground state calculations when you don't know beforehand what's the deformation of the nucleus. If you solve the Hartree-Fock equation for a ground state, it's enough to allow the system to explore the deformation. So you can just choose your initial density with a little bit of some deformation, and then the code will find a solution that minimizes the energy, and it will give the value at the local minimum. Of course, contingent on what we've discussed before, that everything depends on the initial guess. So you have to keep that in mind. Now, in fission, we are interested in, actually, well, we can take this. We are interested in potential energy surfaces. So we want to explore the deformation of the nucleus, and we want to see how the energy changes as function of this deformation. So it's great to have a theory that will automatically tell us some of these deformations, but at the same time, it's not that convenient because it's only going to give us the minimum. What if I don't want only the minimum? I don't want just this point. I want the whole curve. How can I do that? In the liquid drop or Micmac model, you would say, well, just change the deformation of the surface, recalculate, and that's it. But now where are the deformations here? They are an output of the calculation. They are not an input. So the solution to this is to put constraints on the solution. And it requires very minimal adjustments to the equations. The only adjustments is that this term here, oops, is going to be modified by, we are going to add, suppose we want 2 or 3 or 5 or n constraints, so from k equal 1 to n constraints on some expectation value of operators. And so now I'm going to use q as an operator. So this q here, q subscript k, is an operator that somehow will help me constrain the shape. Here is an example of what it could be. So now I'm going to take the operator q. So one example of q would be what is called as the quadruple moment, which is proportional to r squared spherical harmonic. We've seen the spherical harmonics yesterday. So this is the quadruple moment operator. I say proportional because you have different conventions for, there are some different normalization factors you can use. Another one you could use is the octuple moment, which is proportional to the third spherical harmonic. And now those operators, you can calculate their matrix, and this is what I had noted, Qij. This is going to be the matrix in the basis. I think I use 5 for the basis, yes. So so let's say this would be 2, 0 operator. This is the matrix of the operator Q20 in my basis. And if I know this matrix, I can plug it into the mean field, the Hartree-Fock mean field. And that will, again, I sort of go a little fast here, but this will guarantee that at the solution there is, oh yes, and then I will require that the energy, sorry, I forgot that step. I will require that the energy is now becoming, I have to put a constraint on the energy, so let's say E equal E minus lambda Q. Okay, let's try to write it a little bit more, a little bit better. K equal N Q K minus Q. So I'm gonna, and I forgot, of course, I forgot and I think it's a minus here, and I think it's lambda K here. So I'm gonna put a constraint on the energy. I'm gonna put a constraint that the expectation value of my operator has a certain value that I want. I want Q20 equals 50 bounds. That's that number. Q20 is my operator. I can calculate its expectation value using a formula that I unfortunately erased. If I know the density, I can calculate the expectation value of that operator. I will then try to minimize not just the energy as before, but the energy minus this term here. This is the method of Lagrange parameters to solve a problem under constraints. So what you're saying here is, I want now to find the density of particles that is such that the energy is minimal under the constraints that my expectation value of these operators take these particular values. I went a little fast, so I don't know if it's really clear. The Ringe-Schuck textbook has several pages on this, I believe, and this is one of the references that I have in my notes. So with these techniques of putting constraints on the Hartree-Fock solution, we can explore a whole potential energy curve or a whole potential energy surface. If we have more than one deformation, or one constraint, it's going to be a surface. And then we can calculate how we can fix the value of those, the expectation value of those constraints, and calculate the energy at those points, and then make a plot of how the energy looks like as function of this deformation. So this is the analog of setting the deformation by hand in the macroscopic method.
When you say that this allows you to explore more, but let me say, you have to choose anyway your deformation.
Yes. So the big difference is, good question. The big difference is all the deformations that are not constrained are going to take whatever value minimize the energy. In the macroscopic method, all the deformation that you did not set are zero. That may not minimize the energy. You just didn't set them, so they will be zero. But in Hartree-Fock, HFB, and all these DFT methods, all the deformation, all the deformation that you do not constrain specifically are going to take possibly a non-zero value, whatever value minimizes the energy. It means that when you do this in 1D, so let's say now this is, I'm going to try to, let's suppose now that I calculate the Hartree-Fock energy as a function of just a single constraint, whatever that is, it doesn't matter for this discussion. And I'm going to find something like that, just for the sake of argument. But now I will try to plot, and I will try to do it in a way that is pedagogical. So now on a similar type of plot, I want to plot the value of Q prime, another deformation. Suppose this is Q20. This could be Q22, Q40, some other multiple, something else. Whatever that is that I did not, but I did not constrain that one. And this would be the expectation, so this will be given by the trace of this operator times the density matrix. Now, it may be that what I find is that this Q prime varies like that, or any other way. This Q prime will take a non-zero value, whatever value minimizes the energy at any given point here. In a macroscopic method, if I say alpha 20 is my deformation for the surface, and I plot the value of alpha 40, if I didn't set alpha 40, it's going to be 0 always. And that may not be minimizing the energy. Does that answer your question? Not necessarily. Yeah. No. But if you start with, if you start with just a tiny amount of non-spherical stuff, then you're going to get at the end what minimizes the energy, and that could be significantly deformed. But you're pointing to something, because the advantage of self-consistent symmetry, the fact that you can, or the advantage of spontaneous symmetry breaking, as this phenomenon is known, as a sort of reverse aspect to it, if you start with a solution that respects certain symmetry, you're always going to end up with that symmetry. If you start with a solution that is spherically symmetric, you cannot get anything but spherical solution unless you put some constraints. If you put some constraints on, you start with a spherical solution, but you put a constraint on Q20, then you're going to reach that solution that satisfies the constraint, and by definition, it's going to be deformed. But if you do not put any constraint, you rely only on the variational principle, if you start with an initial symmetry, you're going to keep that initial symmetry all the way. Absolutely. Like if you do in lead 208, for example, you do Hartree-Fock calculation in lead 208 or oxygen 16, you can start with a deformation, but you're going to find the lowest minimum, which is actually spherical because it's a closed shell, and it's going to be spherical no matter what. But if you take any random nucleus, then you'll get whatever that nucleus is in its ground state. Yes? The norm of the initial, you mean the norm of the density? It will satisfy, so the density is actually is a projector, so it will keep that property all along by construction. I did not really specify, but when we solve the Hartree-Fock equation, you have to guarantee that only the lower states are occupied. This is a technicality that I swept under the rug, but I don't know if that's what you are asking. Okay. Not, I don't know. I don't know what's... Okay, I can, before we do the break, I will, unless, is there another question? So now, this is Hartree-Fock. Very nice, all great. Lots of problems, by the way, in Hartree-Fock that they did not mention, and I will not mention because lack of time. But Hartree-Fock is not well adapted to describing nuclei that are, say, in between closed shells. Because in those nuclei, we know that there is a phenomenon called pairing correlation that I mentioned yesterday or 2 days ago. That has to do with the excitation energy of the first excited state in even nuclei, that if you have even nuclei, nucleons, protons and neutrons will go in pairs, and that will add binding energy and things like that. You cannot describe this phenomenon with in the Hartree-Fock theory. You need to extend the Hartree-Fock theory to be able to describe pairing correlations. So there are two ways to do that. The historical way is to do what is known as the BCS theory, Barden-Cooper-Schiffer theory. It was invented in 1957. I think I had put that, yes, that superfluidity that we also heard yesterday in Professor Meng's lecture. So initially, I wanted to tell you a little bit about BCS, but I don't have the time, so I'm going to go straight to the generalization of BCS, which is called the Hartree-Fock-Bogoliubov theory. And in fact, to make it even faster yet effective, so this stands for Hartree-Fock Bogoliubov, which has different spelling in the literature because Bogoliubov was a Russian, so his name was originally spelled in Cyrillic Cyrillic letters, and there is no consensus on how exactly it should be written in Latin letters. Okay, so the two theories have a lot in common, and that's why I'm putting them in a table. First of all, let's look at the degrees of freedom of the theory. What do I mean by degree of freedom? Well, in Hartree-Fock theory, everything depends on the density. If you know the density, you can calculate everything at the Hartree-Fock approximation. So in the degrees of freedom for Hartree-Fock is the density matrix. That's it. It's, as I mentioned, you can either think of it as an actual matrix or as a function of R. Again, simplifying a bit because technically it's a function of R and R prime and sigma prime, but okay, these are technicality. In HFB, you still have the density, but there is another object called the pairing tensor. This object is just like the density. You can think of it as a matrix or as a function of R and R prime. This is something that will essentially control the amount of pairing in your system. If the pairing tensor vanishes identically, then you're back with only the density and HFB reduces to Hartree-Fock. Okay, let's look at now the energy. Yes? Yes? It is the, yeah, okay, so if you write down the, yes, so if you write down, oh, I actually did not write down the energy, did I? Oh, I forgot to write, okay, so can I erase this? I think I forgot to write down the energy, the Hartree-Fock energy. So this is gonna be written as, I'm gonna write down the trace explicitly just because it's either like this. You can write down the Hartree-Fock energy using the matrix of your objects in the basis, but you can also write it down in coordinate space, in which case it's going to be written like that. Okay, so T of R, rho, oops, sorry, rho of R, and then I will have then I have to take my notes to make sure I don't make a mistake. And my notes are useless because I did not put that thing in. Okay. So I will probably make a mistake, but no, wait, I can do better than that. Give me one moment. I'm going to your question. That's why I want to address your question. That's a good one. But I need to make sure I don't get it completely wrong. So where is it? I have secret notes that contain a lot more than what I'm telling you. And the reason I have these notes is because I don't remember things. Okay, so Okay, so I think you're gonna get something like this. This is gonna be, damn it. I'm gonna skip some of this. Instead, I'm gonna just say that when I say that the mean field could be written as in coordinate space, it turns out there is another component of this. This one is proportional to the local density only, and this one is proportional to the non-local density, which is written like this, rho ij. This is called the direct term. This is called the exchange term. The direct term is local because it only depends on the density at point R. It's local. This one is non-local because it depends on this density here that now has 2 degrees of freedom, R and R prime. So in configuration space, it's hard to see these two terms. They appear more naturally in coordinate space representation. So it's still, when I say that everything depends on the density, this density, the full density matrix, this is a local density. It's a particular component of the full density matrix. This one is a more general version of it. Now, going back to the comparison between R3-Fock and HFB, the energy which I had written for R3-Fock is now in shorter notations with the trace, is given by this formula. This is the kinetic energy times the density. This is the mean field, gamma, capital gamma, and rho. For HFB is actually pretty similar because it's still trace of T rho plus 1/2 trace of gamma rho. But then there is an additional term, which is trace of an object called delta times the complete conjugate of kappa. And I again want to make sure that I do not, I got the right. The reason why I'm checking my other notes now is because I had not planned to present this the way I'm doing it now. I'm kind of improvising a little bit. So this means I need to make additional checks. Yes. 1 more minute. Almost. Yes, it's almost done. Because this I still want to say about what this mysterious delta object is, and this has to do with your let's say Hamiltonian, and I will put some quote in it because this is not like the many-body Hamiltonian that we had before. This is the H term. That's in the R3-Fock theory. This is the mean field Hamiltonian. It's not the same as the many-body Hamiltonian. Now in HFB theory, I will note it like this. It's going to be H delta minus delta star, minus H star. This little h is the same as the R3-Fock one. You have additional terms that come up. The matrix that you have to deal with is just twice bigger. And of course, I run out of space on this board, so I will have to continue this comparison just before the break on that one. So HFB. The thing that matters is the equation we solve. We've seen that for R3-Fock, it was this commutator. For HFB, it's also a commutator. And now I have to give that last definition. Okay. I explain this and then we take a break. So I mentioned Artifog-Wolibov is an extension of Artifog, and we could spend 2 hours just talking about HFB. Actually, I could spend the whole day just talking about HFB. Here, this is just a table summarizing the main differences, how HFB extends Artifog. It adds a density kappa that will be related to the to pairing correlations. The energy has to be modified. Yeah, there is an additional term which is going to be, in fact, the pairing energy. The equation that you have to solve are going to depend on some mean field Hamiltonian, which now is a matrix that is twice bigger than in Artifog because it has additional term. This delta is called the pairing field. This is the mean field. This is the pairing field. The equation you solve is still a commutator. So in Artifog, it's this commutator between these two objects. In HFB, it's between these two objects, where this mean field Hamiltonian is this guy, and then this so-called generalized density looks like that. And it sort of encodes both degrees of freedom in a single object. Other than that, the way you solve the equation is pretty much like Artifog. You would try to find a basis that simultaneously diagonalize these two objects, and you would essentially have the same kind of self-consistent loop as before, except that now you also have to specify an initial guess, not just for the density, but for kappa, or alternatively for this generalized density. So you would take a guess for the generalized density, calculate your big H from there. Yes, that's how I realize that I still forgot something. This delta is related to your pairing tensor and your matrix elements of your two-body force. This is what I had noted, IJ, V, K, L. So that's this object, and it's related to via this relation. Okay, and now we can make a break because I definitely need a break. I'm sure you do. 10 minutes. Okay, so we're gonna start over. One last thing about the difference between Artifog and HFB. In Artifog, I was mentioning the possibility to get deformation emerging from the calculation, and I briefly mentioned the word spontaneous symmetry breaking. That if you start with just a tiny bit of deformation in the initial guess, you would find whatever minimum minimizes the energy, and that could have a significant deformation. So this means that Artifog theory, you can or not, depending on the nucleus, you can break rotational invariance. So if we think about broken symmetries, the one that can be broken, again, it's not necessary because it depends on the nucleus. In lead 208 or oxygen 16, it's going to be spherical. But in other nuclei, you can break rotational invariance. There are other symmetries. If you have a shape, if your Artifog solution leads you to a shape that, say, has a non-zero octuple moment, your shape is reflection asymmetric. It breaks parity. Parity is not conserved anymore. So this is another possible symmetry that you can break. One thing that people always forget is when you solve your Artifog solution, you tend to fix the center of mass of the system, which means you break translational invariance. And so that's yet another translational invariance. But in H, so this is for Hartree-Fock. There is yet another one, which is time reversal symmetry, which has to do with odd mass systems. I don't want to discuss that for now. In HFB, these ones, exactly as in Hartree-Fock, plus there is another symmetry that is broken, potentially. If this pairing field is non-zero, that is, you have a solution with pairing correlation, there is an additional symmetry that is broken. I can ask what it is, but if you're not into this, I don't know if you would be able to guess the answer. But you are into this, I know. Oh, I forgot isospin. Yeah, but no, not isospin. Particle number, yes. So if you you can show that the many-body wave function at the HFB level, so at the Hartree-Fock, it was a single Slater determinant. You can show that at the HFB level, it's not a single Slater determinant anymore, it's a superposition of them with different number of particles. So your HFB wave functions I'm going to continue here, again, the comparison. So I can formalize this by saying that if I take the number operator, I'm not even going to give you what it is. If you're into second quantization, you know what the form of this operator is, but you can say that the Hartree-Fock wave function, the many-body wave function, the Slater determinant, this is an eigenstate of that number operator. In HFB, that's not the case anymore. The HFB many-body state is not an eigenstate of the number operator. That's an additional symmetry that is broken. That is actually a problem, because it means that when you study a nucleus at the HFB level, technically you're never studying, let's say, I know, plutonium-240, my favorite nucleus, but you're studying a superposition of plutonium-238, 239, 240, 241, a certain superposition of them. There is additional things we could say about this, but I'm going to skip that. All these symmetries, this is the price to pay for Hartree-Fock or HFB to be good theory. They actually do pretty good in terms of predicting nuclear properties. But the price you pay by using this theory is that you're breaking the symmetries that we know in nature are conserved. I mentioned that yesterday. A nucleus has good angular momentum. Experimentalists measure it every day. So when we say that angular momentum is not conserved because rotational invariance is broken, this is a crime. This is not true. So we are introducing those symmetry breaking concepts in order for the theory to do a better job at reproducing things like energies or radii or things like that. We will see tomorrow, or probably actually on Friday, that we can restore those symmetries. We can recover those quantum numbers that we are losing. If rotational invariance is broken, that means no angular momentum, so we cannot label states with good J. You can recover that by using techniques called projection techniques, but this is an additional complexity. Okay. Yes. Yes. That is absolutely correct. Yes, but the good news is that many of them, or the good news or bad news, are very easy to break. If you want to break rotational invariance, any multiple moment, you take any multiple moment, you put a non-zero value somewhere in the matrix of that operator, and that's enough. And it will make the system potentially deformed. For a particle number, that's actually a good point. For HFB, if you start, this would be, for HFB, it means that if you start your self-consistent loop with a pairing field that is zero, identically zero, it's always going to be zero because that matrix is going to be diagonal and you're basically going to solve R3-FOC. But if it's enough to put one element of this matrix non-zero to get the full glory HFB equation and get n pairing solutions, yes. Yes, that is correct. So in HFB, you could do a very convoluted approach and say, I'm going to initialize my HFB calculation with kappa equals 0, but then I'm going to put a constraint on something, which in fact would have to be kappa, but to enforce that I still get a solution with pairing. So this concepts of symmetry breaking, this is a cornerstone of energy density functional methods. If you remember where it comes from, the R3-FOC and HFB, yesterday I was talking about many-body Hamiltonians. We have a Skirm force, Goni force, covariant density functional theory that we heard also. Those are phenomenological models of nuclear forces. The real nuclear forces inside the nucleus are not really like that. These are approximations. Because of these approximations, we make another approximation when we take the R3-FOC many-body state, or the HFB one. They are not the eigenstates of that many-body operator. So we are making two approximations, or Hamiltonian is not the real one, although to be fair, nobody knows exactly what the real nuclear many-body Hamiltonian is, but if we don't have the real nuclear many-body Hamiltonian, and we are not anyway getting the real many-body wave function, we are taking an approximation of it. In order for these two combined approximations to work, we have to introduce this symmetry breaking. And when, yes? Excellent question, thank you very much. Yes, we can. We can, and in fact, when you solve the HFB equation, there is an additional term that comes here, which is interpreted as the Fermi energy. And this term, this is a number, lambda is just a number. And so in other words, it's a diagonal matrix if you want. And this Fermi energy is the Lagrange parameter that will guarantee that the average particle number is conserved. We still don't have an eigenstate of the particle number operator, but we can make sure that on average, so that means something like this, which is this, is equal to whatever value we want. So it's not exactly the same as having an eigenstate, but it's better than nothing because at least we know that we have, the average number is correct. So in the context of fission, what we need now is to get so in the macroscopic methods, since we were, I had mentioned on Monday that following the insight of these two guys, fission is a deformation process. So in the microscopic methods, those deformations are going to be the deformation parameters of the surface, of the nuclear surface, and they will allow us to calculate the potential energy as a function of this deformation. In the HFB framework, those deformation parameters are going to be the constraint operators. They are going to be operators. We're going to put constraints on the expectation value of these operators, and that's how we are going to define our potential energy surfaces. Those deformation parameters in the rest of this week, I'm going to call them collective variables. Okay, collective. Why? Because since they are not on the blackboard anymore, but these constraints, they involve these are expectation values, so they involve all the nucleons. So this is why it's a variable, because this is something that we will use really to calculate the energy as a function of those variables, but they are collective variables because they represent something that is associated with the entire nucleus. So collective in nature. So to recap, The collective variables in the MICMAC model are the deformation parameters of the nuclear surface. In the HFB theory, it's going to be the expectation, it's going to be the constraint operators that we want. So before I say a few more, now I want to show a few slides to take a break. So here is, so this is a couple of slides to illustrate those hardcore concepts. This is an example of nuclear ground state deformations. So on the left is a MICMAC model, microscopic model. This is the famous one, the finite range droplet model. It's essentially what we described yesterday, but a little bit more sophisticated. This is the equilibrium deformation. Actually, it's the deformation. This is the value of the quadruple deformation, which is denoted by epsilon 2, at the minimum of the energy. So what the people in this, what they did in this paper, they defined a parameter space. I think they may have decided like 3 or 4 different parameters for the nuclear surface. They calculated the leaky drop plus shell correction energy in that deformation space for every single nucleus. They identified where the minimum of the energy was, and then they plot the value of the ground state quadruple deformation for each nucleus at that minimum. And they get something like this. So in blue is the, it's 0. And so you recognize the closed shells. It's conveniently indicated by those lines. So at the closed shells, you know, oxygen 16, lead 208, tin 100, tin 132, and so on. Those deformations vanish, so it's good. The model indeed tells you that, well, the minimum for this nuclei is indeed spherical. That's great. And then you have regions of, this is the absolute value of the deformation, so we cannot distinguish between prolate shape, which would be like this, and then oblate shape, which would be more like this. So oblate shape is like a rugby ball, and oblate shape is more like a flattened thing. But okay, we can do these kind of large-scale calculations. That tells you that most nuclei are deformed in their ground state. As a comparison, here is a a mean field, well, I'm getting tired, an HFB calculation. An HFB calculation with a particular parametrization of the SCUM potential. There are plenty others on the market. This is the one I took from this website. It shows, I believe, the same quantity, namely the ground state quadruple deformation across the nuclear chart. And on the one hand, it's similar, but on the other hand, it's not the same. And if you take different SCUM forces, or if you take, there are several parametrizations of the Goni force, or if you take a covariant DFT, you will always get different results. They're going to be similar. I mean, you will get the closed shells. Yes, oxygen 16 is always going to be spherical. But the value of the deformation across the mass table, across the chart of isotopes, is going to change depending on the model. So there is a sensitivity of your calculations on which model you use. It's an endless source of arguments between theorists. Which one is the right one? Of course, experimentalists come and say, well, the data is whatever it is, but so this is an illustration of how your deformation properties, even in the ground state, are going to be dependent on your favorite model. And if you think that there is dependence in the ground state, imagine what it is when you now look at a very deformed shape. And is that what I have in the next slide? Yes. So now, let's probe a little bit more. Let's try to stretch the nucleus a bit more and see how the predictions change as a function of deformation. So this is taken from one of my older papers. This is a bunch of different SCUM functionals, because back then I was mostly doing calculations with SCUM functionals. 2 different nuclei, neutron deficient isotope of lead, and then the uranium-236. And what we plot here is the deformation energy, so the energy with respect to the spherical point. So all the curves go through the spherical point, and it's plotted as a function of the axial deformation beta 2. This is an HFB calculation, so if you're very, very smart and paying attention, you are wondering how you can get a deformation parameter from an HFB calculation. this is extracted from the expectation value of the quadrupole moment. It's not something you put by hand, it's something that you extract. You get the calculation as putting a constraint on Q2, and then or Q20, and then you extract using some formula what is the equivalent deformation that you should get. And what is pretty impressive here is that the results are all over the place. And every one of the people who came up with this parameterization of the Scum force, they would tell you that this is a very good parameterization. It's working very well. But they give very different results. And this is, this is the ground state. For this lead isotopes, it's actually spherical. There is an isomer here, a shape isomer. For uranium, the ground state is deformed, but the value of the deformation energy varies quite a lot. But wait, there is more. It gets worse. This plot is by one of my former postdocs, and what he did is he calculated. So let's look at this one first. So this is the potential energy curve in plutonium-240. It's my favorite nucleus, as a function of the quadrupole moment. So the energy as a function of the quadrupole moment for one particular energy functional, a Scum functional again. The blue curve is like what comes out of the box. You do the HFB calculation with that Scum functional, and you get the blue curve. But back then, what we tried to do, we tried to quantify the uncertainty of this calculation. Specifically, this functional, just like all the other Scums, it has about a dozen parameters. We can do something called a Bayesian analysis to extract the posterior distribution of those parameters. I don't know exactly how much you know about statistics and Bayesian and statistics and things like that. Essentially, you can treat every one of these parameters as a random variable and get its probability distribution. And if you have 12 variables, you have a 12-dimensional probability distribution. And then you can try to say, okay, what's the most likely, what's the confidence region, the 90% confidence regions in that 12-dimensional space. You can sample this confidence region and you get the gray band. This is a huge difference. The plutonium-240 can spontaneously fission. It can also, it's more interesting mostly because of induced fission, but it can go through spontaneous fission. The spontaneous fission that you get if you take the height of the barrier here or here are going to vary by dozens of orders of magnitude. So it's a big difference, big uncertainty, just because of the way this functional was fitted. This illustrates different functionals. This illustrates a single functional, but trying to quantify the uncertainty caused by the fit of the parameters of the functional. And then here is another example of calculating this fission barrier. This is the first one. So this is the height of this barrier. So this is a difference between this point and this point. For different actinide nuclei, using, I forgot to put the legend, but using each curve, each point, each color is a different functional. And it's not just Scum here. There is a few Scums, there is a Goni functional, and I think there is even a macroscopic model calculation. And again, the height of this barrier vary between, quite a lot between functionals from, say, in this case, plutonium 5.5 all the way to, 7.5. That's a huge variation. Here is another series of plots showing more of the same. This is a simpler version of that, where they also try to quantify the uncertainty of their calculation for the barrier. This is more statistics for this one is the fission barrier for a super heavy nucleus. The height of that first barrier, depending on which model you are using, is it a Scum functional? There are different versions of it. Is it covariant mean field, covariant density functional theory? And again, it's all over the place. Sensitivity of your deformation properties on the nuclear potentials that you are using. The theory, the way these things were calculated, this is all HFB theory. It's the same kind of calculations. The only thing that changes is which energy functional, so which, it's not anymore in the blackboard, but this is the potential V that I was showing before, the many-body potential. Yes, that's. No. This the fitting procedure is these two plots. They quantify the uncertainty caused by just the fitting procedure. Yes.
So that's very interesting. Anything you want to mention? Because
S-
some interaction are fitted on, say, on infinite matter properties, other are fitted on. So it's
So this would be reflected, for example, in this curve, because these are all different skirms, and I don't remember on top of my heart, but I think they are pretty much the same skirms, but these two, SKI3 and 4, are coming from the same group with two different fitting strategies. SKM star is yet another one. It's an older one. SAY4, SAY6, they're actually different functionals. They are, yeah, it's skirm, but they have different components. But you're right, yes, there is. What is the form of your two-body potential? Is it skirm, goni, covariance? Even within each family, there are variations. So there are different types of skirm. There is skirm without tensor terms. There is skirm with tensor terms. So, okay, same thing with goni. Same thing with covariant DFT. We've heard that there were meson coupling, density-dependent coupling. So there are different flavors of the same family. Once you've chosen your favorite functional, you have to come up with how you're going to fit the parameters. We also heard about it yesterday from Professor Meng's lecture. You have to decide which nuclear properties you're going to use, which chi-square you're going to build, how you're going to minimize that chi-square. Once you've done that, you still have to do this Bayesian analysis or this version here, which is simpler, which is just covariance analysis. All of this, each step is giving you additional uncertainties. And the elephant in the room is all these calculations are done on a computer, typically by expanding things on the basis. And when you expand on the basis on a computer, you cannot expand on an infinite basis. You have to truncate your basis. And all these calculations also have a numerical error that nobody ever tries to really quantify because they would be scared. So dependency on deformation properties. Yes. So that's a very good question. There are debates about what exactly, it's about which fitting procedure you have to take. In principle, from a pure mathematical perspective, you could say I have, let's say, 10 parameters. If I have 10 points, that's enough. But then you want to make sure that your functional will have predictive power for different kinds of nuclear properties. So one difference, for example, between this functional and these families, these all actually, no, sorry. Well, let's look at this one. These are historical ones, and I was not involved in any of them, so I can criticize them. So these SKO, SLY 4, 6, and SKI, they were fitted, if I remember, only on spherical nuclei and nuclear matter properties. SKM star was also fitted on the height of the fission barrier in plutonium-240. So something different that this unit F1 that I was involved in was also, we also fitted this quantity here, the height, the excitation energy of the fission isomer. So the motivation is if you use in your set of experimental data that you use for the fit, I personally believe that you should try to use data that will allow you to probe different regimes in which you're going to do your HFB calculation. If you want to use HFB calculation in deformed nuclei, I think it makes sense to try to include deformed nuclei in your fit, because otherwise you don't. It's hard to guarantee that it will work. You have to make a leap of faith that everything else will be well constrained. There are arguments of, there are pros and cons. There are people who could tell you pretty convincingly that nuclear matter is sufficient. It's an ongoing debate. Let's put it like this. Yes, that's correct. It's doable. I would disagree with that because since I've been pushing those efforts, so it works pretty well. But I don't know in the covariant DFT world how it works, but this in the SCRM, so that also goes back to why you should choose one functional versus the other, because some of them you can do calculations faster, and that has advantages, because if you want to include deformed nuclei, that's going to make calculations easier. So this UniDev1 was fitted, it's a SCRM, but it was fitted using deformed nuclei, actually several deformed nuclei. So the thing is, if those deformation properties, they are not just abstract, they have consequences. The consequences are now, if you go back to the beautiful world of fission, and we look at some properties here, these are the fission cross sections. The fission cross section, if you remember, it's the probability that the nucleus will fission relative to other mechanisms by which it could decay. And so what those plots show, these are taken from these two papers. This is a plot of the fission cross section in this particular nucleus, where the only thing that was changed between the calculation, you don't know yet how we do these calculations. I'm going to say a few more words about it later on, but those calculations depends on the height of the fission barrier. And so the black curve is what if you, I will start with this one. The dashed blue curve is what you get if you take a parabolic barrier, an inverse parabola, that is controlled by a height and a width, and you fit those parameters to some data, and you get the dashed blue curve. If you do exactly the same calculation, but the only thing you change is the barrier, and you take it from an HFB calculation, you get the black curve. Now, I will let you decide which one is the best. That I don't care. What matters is that there's a big difference between the prediction of the fission cross-section. So those deformation properties, they have an impact in real-world applications, to say, because when you use them to calculate your fission observables, they lead to uncertainties in those calculations. This is more of the same. This is the same kind of thing in this particular nucleus, where you see the beautiful data that we have to deal with. And then this is yet another example from this paper, taking the sort of baseline as the best barrier that they could come up with. That's the red line. And then adding just 100 kV to that height. It's not much. It's really not much, especially considering if you were doing a numerical calculation, 100 kV is easily your numerical error, easily. And just 100 kV, I mean, yes, that doesn't change this one too much, but these two, they are changed by at least a factor 2. So the sensitivity of your nuclear models, the fact that your nuclear theories predict rather different, quantitatively different deformation properties, even though qualitatively, again, all these models agree. Most of this model would agree of which nuclei are deformed, which ones are not. But when you look in the quantitative details of their predictions, there are uncertainties, and that leads to consequences. Okay, so one last word before I conclude this part, which was supposed to be concluded yesterday, but it's the calculating these potential energy surfaces that I was mentioning. I said, oh, you want to set up which deformation parameters you need for the MICMAC model. How many deformation parameters do you need? You want to decide which operators are going to be used as constraints on the HFB solution. So one choice is like the physics of each of these parameters. You want, we talked about it, I think, on Monday. You want parameters that can describe reflection symmetric shapes, and other parameters that can describe reflection asymmetric shape. Since fission is a deformation process, you want something that can describe that elongation phase. You also want probably something that can describe the neck between the two pre-fragments. So you need a few collective variables, deformation parameters or constraints. But this has a consequence. If you just do very simple estimate, let's say that you take Q20, which is the axial quadrupole moment, and in the MICMAC world, actually I can say this is HFB, and then this is MICMAC, macroscopic. This would be corresponding to this alpha 20 parameter. And the physics of this is that this gives you the elongation, this control the elongation of the nucleus. And since you want to elongate the thing until it breaks, you definitely need this guy. We've also mentioned that Q30, which would be typically this, will control the mass asymmetry. And you need this because you want to be able to produce a heavy fragment and a light fragment. If you don't have this type of parameters, you're never going to get different fragments. You're always going to get fragments that are the same. We could continue. We could say perhaps we need Q40, which the advantage, this is why I chose, by the way, this, if you remember, this multiple expansion of the radius. That's the reason I chose this particular parameterization of the nuclear surface in this lecture, is because there is a nice mapping between the multiple operators and the parameters of the multiple expansion. So this is kind of controlling the degree of necking between the two fragments. So if I have two fragments like this, and they are separated by a neck, Q40 is going to sort of control a little bit how thick that neck is, kind of. And there may be others. Now the question is, how many points do you need? If you put constraints on this quadruple moment, you have to set the value of the constraint. So how many different values do you need to consider? For fission, which I don't know if I have it anywhere here, we can take this figure as a guideline. You have to be able to map this whole curve, and believe me, we are far from scission here. We are halfway through scission. So how many points do you need? Well, this is these are going to be estimates. It's orders of magnitude, but at least more than 100. For the elongation, more than 100. Of course, the more the better, but the point of this little exercise is to show you that the number of calculations you have to do increases substantially very, very quickly. Mass asymmetry, I don't know, 50. And then Q40, it's up to you. Let's say just 10. Now, how many points do you have to calculate in total? 50,000. 50,000 different calculations for every one of in this cube of deformation space. The naive estimate tells you that if you just have 3 degrees of freedom that control the deformation of your nucleus, if you want to map out the potential energy of that nucleus, you would have to calculate 50,000 configurations. In the macroscopic microscopic method, that means you solve the Schrödinger equation 50,000 times for each of these deformations, and then you calculate the liquid drop energy and so on, or you do 50,000 HFB calculations. Time of calculation. Time of calculation, again, these are very rough order of magnitude. Micmac model, oops, sorry, this should be, so a Micmac model, I guess 1 minute is, these days, you can probably do 1 minute for whatever shape you want. It doesn't take very long to do these calculations. For HFB, it depends. All these deformations have also the property, if you remember what I mentioned yesterday, that they are axially symmetric. So the time of calculation for an axially symmetric, HFB calculation, this is, let's say 10 minutes. 10 minutes for a skirm. I think on using some parallelism, you can also do 10 minutes for a Goni force. For covariant DFT, I don't know. It's perhaps a bit longer. It depends on your numerical precision anyway. But if it's, so this is for axial calculation. If it's not axial, which by the way is another parameter you have to explore, because the height of this fission barrier, this one, is extremely sensitive to the degree of triaxiality of the shape. It will decrease if the shape is triaxial. So if the calculation is not axial, then anything more than 1 hour. And now, yes, 50,000 calculations, each of them takes 1 hour. That becomes a non-completely trivial computational problem. Yes. Oh, this would be for typical like heavy nucleus, plutonium or something. The only nuclei that fission are the ones that are heavier than lead. So you need to be able to describe systems that are heavier than lead. So this is all for a single nucleus. Because now, if you want to do this calculation, all this calculation that he did here, it's for different nuclei. So you need to multiply that by the number of nuclei you want to study. But for every single nucleus, assuming these are very simple estimates, I insist, it's not very rigorous. And these estimates of time of calculation will depend a lot on the numerical precision, the type of functional you are using, which computer you have access to, how much parallelism you have put in your codes, are you using GPUs and whatnot. But these are sort of ballpark estimates. So that's one of the last thing I wanted to mention is the scope of these calculations. Professor Meng mentioned 2 days ago, I think, that DFT is a theory for poor people that don't have a lot of computational resources. I agree. You can do DFT calculations on a laptop. You cannot necessarily do 50,000 DFT calculations on a laptop. So for some of the problems that only DFT can tackle microscopically, like fission, you need supercomputers. And that opens a can of worms, because now there are people who like that, but you have to be able to use the supercomputers, and usually they come with some requirements and things like this. Okay. Okay, so then I will finish a little bit by let's say, yes. So I will finish by mentioning quickly one thing that I had not really I have swept under the rug until now. I did mention earlier the concept of fission, the point where the nucleus splits in two. What does that mean exactly? The point where it splits in two. So here is an illustration in the context of the MICMAC model, so microscopic methods, where you set your surface by hand, right? You set the parameters of the surface. I was talking about the multiple expansion of the radius. Again, the reason I chose that is because I can easily compare the HFB and DFT world with the MICMAC world, but it's not the best expansion of the radius if you're interested in fission. And people have used different parameterization. So this is taken from one of my papers, review papers. These are different. This is the same model to describe the shape, but here we apply it in a case where we want a reflection asymmetric shape, and here when we want a reflection symmetric shape. Now, some parameter is varied. This would be the point of fission, right? So you have a shape like that, that's this dashed line, dashed green line, and there is this point, this literally a point of fission. Do you think that's really very realistic for a physical system to be like that? That doesn't, like, what's the likelihood that you can really make any quantum mechanical system look like that? It's not very realistic. In fact, when people do calculations, they realize, oh yeah, that's not realistic. The system will scission before that. So it will scission instead like this. That doesn't seem very realistic either. So this is a problem that the point of scission is an extremely ambiguous concept. It's the point where everything is decided, because that's the point where calculations stop and we say, yes, the system has split in two. But quantum mechanically, it's not very easy to decide what exactly it is. So in those microscopic methods, they come up with shape parameterization that allow them to identify a point like this, or they will take whatever shape they produce and then they cut it and say, that's the left fragment, that's the right fragment. Right, it has this kind of straight line, but you have to do something. In the HFB world, we try to do something a little different because there is no way we can produce either this or that. So we try to put, people have come up with different concepts to define what scission should be. None of them is, perfect, or none of them is in fact very good, you could say. So this is the concept of scission. So again, you have a shape like that and a shape like this. Oops. And then there is a neck between them, some kind of neck. So let's say that you can produce a shape that looks more or less like this by putting the suitable constraints. And then you can say, all right, I have an axis here, which is my z-axis of my intrinsic reference frame. I can find this point. It doesn't necessarily coincide with the origin of that reference frame, especially if you have a heavy and a light fragment. But I can find this point, and I can say the point of scission is, I don't know, let's say I take this z here, and I can calculate the expectation value of this particular operator, which is z minus zn. This would be zn divided by some range square. And I can try to calculate the expectation value of this guy in the HFB state. And what it does, it kind of counts the number of, well, it's a way of estimating the number of particles in a small region near the neck. That will depend on this completely arbitrary range, A. If A is large, then you're going to try to expand that range around scission. If A is very small, you're going to really look only at this part here. You can then decide that scission is when Qn expectation value, so this means the expectation value of your operator on the HFB state, so this would be something like this, HFB. And then you can say, well, let's say it's lower or equal than something, some number, I don't know, x. All your calculations, all your results will depend on, so that would be the definition of scission. That's one possible one. That means that all your results will depend on that criterion that you have chosen completely arbitrarily. Should x be 1? Should x be 2, 3, 0.1? Who knows? Your predictions are going to be dependent on that. That's one option. People have decided they also looked at different criterion. Another one was simply to take the density of particle at the point of the neck and say that this density should be lower than some epsilon, which again has to be set by hand. You has to choose it. How? Why? This is not something you can measure. And yet all your calculations will depend on that choice. So this is a problem with the concept of scission. In these calculations, everything I've talked about right now, it's purely static. We are trying to describe a time-dependent process. Fission is something where the nucleus deforms and split. It's time-dependent, but we are trying to describe it in a purely static way. And when we do this, we have to introduce this concept of potential energy surface so that we explore all the different shapes, and then say that at specific points on those shapes, these points defined as the scission points, then the system has indeed formed two fragments. This is bad. So there is an alternative to this, which we are going to see probably on Friday, which is time-dependent density functional theory, where you let the system evolve in time, and it will by itself very nicely split in two. This is because the theory is time-dependent. When you do static calculations, you have an issue with the definition of your scission configurations. And I'm almost done. I just want to finish with the takeaways for this third day, which, well, third and also yesterday. So the few takeaways. The first one is, this was mostly discussed yesterday, that we have two main contributions to the total deformation energy. There is a leaky drop contribution, and there is contribution from shell effect. If you do an HFB calculation, all those contributions are sort of blended into the HFB energy itself, but they are still there. You can still sort of distinguish between things that behave more like a leaky drop and things that really come from the single particle levels of the nucleons. So that's one thing. The second thing is deformation is model dependent. This is model dependent because it depends on whether you do an HFB calculation or whether you do micmac, which operators or which parametrization of the nuclear surface you are using. So all of that is model dependent. And as I mentioned also a couple of times, if you do not do DFT or micmac, but you do shell model, couple cluster, in medium similarity renormalization group or any of these many-body methods, you don't need deformation at all. So this is a very model-dependent concept. Yet fission, the way we understand it, that's the third takeaway, is entirely driven by deformation, by this model-dependent concept. And then the last takeaway was potential energy surfaces calculation that will allow us to really compute those fission observables. They are a computational challenge. And on this note, I think I can finish. Thank you. Questions? Do you have time for a couple of questions, or everybody wants their coffee? No, okay. Question first. Oh, yes, yes. So this is what we had discussed yesterday or the day before, is that you're going to look at, you're going to make, let's say, suppose it's a two-dimensional calculation, and as a function of Q20 and Q30. This controls the elongation, this controls the mass asymmetry. And you calculate your potential energy surface, and then you, whatever criterion you want, you find that there is some scission line that is the point at which this criterion is satisfied in that two-dimensional space. This would be 0 here. Here, you will have reflection symmetric shape because Q30 is 0, which means your two fragments are going to be identical. That is visible experimentally. You have two fragments. It's the symmetric fission I had alluded to. If your system comes out at that point, it will be symmetric. If it comes out, let's say, at that point, it will have a non-zero value of Q30, and so you will have a big fragment and a small fragment. And by considering all these options here, and what we'll do tomorrow or the day after, is I'm going to present a way to estimate the probability that it comes out here or anywhere else. And by folding these two, calculating the probability that it has this shape, and actually computing this shape, we can match that with experimental measurements, in particular those yields. Yes. You can always ask me questions at the break or later in the afternoon, at lunch, or anytime.